Representations of functions as power series. Using the geometric power series. In this section, we will learn that you can represent certain functions as a power series by differentiating or integrating the geometric series for 1 over 1 minus x, written in summation notation as the sum of n equals 0 to infinity of x to the n, or expanded out, it looks like 1 plus x squared plus ... with the general term being x to the n, because here, to get from one term to the next, we're multiplying by that common ratio of x. Here's the main theorem we're going to be using in this section. If the power series, the sum of c sub n of the quantity x minus a to the n, has a radius of convergence, capital R greater than 0, then the function defined by f of x equals that power series, so here it's just written expanded out, or equals that summation notation version of that power series. Well, that function represented by that power series is differentiable, therefore we know it's continuous, on the interval a minus r to a plus r. So open parentheses here, because we just know the radius of convergence is r, so the center is a. So to the left r units and to the right r units, but we would still need to check the endpoints. And we're going to be talking about the derivative of f of x and the integral of f of x. So if f of x can be represented as a power series, then f prime of x can be obtained by differentiating each term of the power series. So the derivative of c sub 0, a constant, is just 0, so that's why that c sub 0 term is gone. The derivative of c1 times the quantity x minus a, well, that would just be c1, because if I distribute this c1 into each term, the derivative of c1, some constant times x is the constant, and c1 times a, that's a constant, and its derivative is 0. And then we can take the derivative of the next term by doing the chain rule. So we can multiply that 2 to the front times the c2, leave the inside the same, reduce the power by 1, so that's why it becomes to the first power, and the derivative of the inside is just 1. So we can differentiate term by term, so this would be the derivative of the next term by the power rule, and in general, I can differentiate the general term here by dropping that n to the front, multiplying n times c sub n, leaving the inside quantity the same, x minus a, and then to the power of n minus 1. So I'm subtracting 1 from the exponent every time. And a slight thing we want to notice here is that the starting index changed from n equals 0 to n equals 1. And the reason for that is because we're losing the first term, because the first term is a constant, and when we take the derivative of a constant, we get 0. So we're starting at the next term, n equals 1. And we can also integrate f of x. If f of x is expressed as a power series, we can do term by term integration here. So here, remember that our general antiderivative, our indefinite integrals, require a generic constant. So I'm putting that constant in the front here. And then c sub 0, we would include that term, quantity x minus a, from the power series form. And then here, if we add a power and divide by the new power, so we have x minus a to the second over 2, and then here, x minus a to the third over 3 plus ... so this is an infinite power series. Or in the summation notation format, we're going to leave that generic constant on the outside, and then we can write it as the sum of n equals 0 to infinity of c sub n, and then what do we do with our general term integration? Well, we add a power, so x minus a to the n plus 1 over n plus 1. And that starting index did not change because for integration, we simply add that generic constant term. Right? But differentiation, we lose the first term when we take the derivative. So, in other words, to summarize, we can differentiate and integrate a power series term by term. We can do it one at a time, term by term, to obtain a new power series, each with the same radius of convergence of the original power series for f of x. But the endpoints need to be checked. because the interval of convergence may or may not include the endpoints. In this example, we want to find the power series for f prime of x and f double prime of x and state the radius of convergence for each, given that f of x is equal to 1 over 1 minus x, which we know can be represented by this power series, 1 plus x squared. In general, the sum of n equals 0 to infinity of x to the n. But we know that this power series only represents 1 over 1 minus x on its interval of convergence from negative 1 to 1. So that means that the radius of convergence is r equals 1 for this power series. So we want to find the power series for f prime of x. So here, f prime of x would be equal to taking the derivative term by term for the given power series. So the derivative of 1, a constant, is 0. So when we take derivatives, we're losing that first constant term. The derivative of x is 1, and then we have 2x plus 3x squared plus plus the derivative of x to the n is nx to the n minus 1. So we're doing the power rule there. So here we can write the general term. If we start at the index of n equals 1 to infinity, of that general term, again, x times n times x to the n minus 1. So that general term here. So we should, just at least mentally check that this works. If I substitute in a 1, then I'd have 1, and then x to the 1 minus 1, well, that's x to the 0, so I do get out my first term here. If I plug in 2, I'd get a 2 in the front, and then x to the 2 minus 1, so that's just 2x. So I can see that this works, and when I take the derivative, that's when my starting index moves up by 1. And we know that the radius of convergence will be the same as the original function f of x. So my radius of convergence will still be r equals 1. And then for f double prime of x, we can do the same thing. So f double prime of x, we can do the term by term differentiation. So 2 plus 6x plus ... because the derivative of 1 is 0, and taking each term separately. Now here, when I attempt to do the general term, I'm going to, again, take the exponent, multiply it to the front. So I'm going to write that as n times the quantity n minus 1 times x to the n minus 2. So I'm subtracting 1 from the exponent here. So this would be the general term, which helps me write the condensed format, the summation notation, which will start at n equals 2. So anytime I differentiate, I'm going to move that starting index up 1. So n equals 2 to infinity of that n times the quantity n minus 1 times x to the power of n minus 2. And again, that radius of convergence is going to be 1. That radius of convergence is going to be 1, but we don't know the interval of convergence without testing the endpoints. But we're only asked for the radius of convergence. In the next few examples, we're really going to have to know our relationships between a function, its derivative, and its integral. So here we're asked to find a power series representation for f of x equals 1 over 1 plus x, and use it to obtain a power series representation for g of x, which is 1 over the quantity x plus 1 squared. So we need to find, eventually, the relationship between f and g, and then find the interval of convergence for g. Let's start with the power series representation for f of x, 1 over 1 plus x. So f of x is 1 over 1 plus x. I want to think about that as 1 over 1 minus negative x. So I have my general a over 1 minus r form. So that means that my starting value is 1, and my common ratio is negative x. So I'll just write out a few terms of the expanded version. So we'll start with 1, then multiply by negative x, then multiply by another negative x, so plus x squared. Another negative x will give me minus x cubed, and then plus x to the 4th, plus ... So I'll hold off on the general term until we write the summation notation or the series notation. So I want to write this as the sum of n equals 0 to infinity of the general form of a geometric series, which this represents, is a r to the n. Well, a was 1, so this would be 1. The common ratio was negative x, so we have negative x to the n. So this right here would be my general form, so my summation notation for this power series. So this is my power series representation. And here, if we wanted to think about the radius of convergence, or even more specific, the interval of convergence, since it's geometric, a geometric power series converges whenever the absolute value of the common ratio is less than 1. So the absolute value of negative x, well, that's just x is less than 1. So my interval of convergence is between negative 1 and 1. But this is all for f of x, 1 over 1 plus x. So what we want to do is use this power series representation to find a power series representation for g of x, which is 1 over quantity x plus 1 squared. So we need to think about how are f and g related to one another. And we should be thinking related through either differentiation or integration. Well, to get from f of x to g of x, there's going to be a derivative involved, but it's not quite perfect. So f prime of x, the derivative of 1 over 1 plus x, is actually going to be off by a negative for this g of x function. So f prime of x is actually negative 1 over 1 plus x squared, right? If we bring the 1 plus x to the top and make it 1 plus x to the negative 1, bring that power to the front, reduce the power by 1, I'd get negative 1 over quantity 1 plus x squared, or x plus 1 squared. So here, f prime of x is equal to not quite g of x, but negative g of x, right? Negative g of x. Or another way to think about that is that g of x is equal to negative f prime of x. Well, we have a power series representation for f of x, and so we can just take the derivative of each term one at a time and then multiply by a negative, multiply everything by a negative and distribute it in. So let's go ahead and start to kind of write things out. So we really want the power series representation for g of x. But remember, that's equal to negative f prime of x, or negative of, and I'm going to go ahead and start writing out f prime of x. So I'm going to take the derivative term by term up here. So the derivative of 1 is 0, the derivative of negative x is negative 1, and then we have plus 2x, so this piece right here, and then minus 3x squared, the derivative of this piece, and then plus 4x cubed. Then it's going to be dot dot dot. And then if we do the summation notation version, so I'm going to go ahead and make sure I include a negative in the front, and then take the derivative of my summation notation version. So here we are going to lose that first starting index, so we'll start at n equals 1 to infinity. And then here we're going to go ahead and take the derivative by bringing the n to the front through multiplication, n, then we have negative x to the n minus 1. So we've applied the power rule, but the inside is negative x. The derivative of the inside is a negative 1. So we're going to have this extra negative 1 on the outside. So this negative and this negative are actually going to cancel, so I can write this as the sum of n equals 1 to infinity of n, and then quantity negative x to the n minus 1. Or I'm going to give you an alternative way of thinking about this. So this is negative 1 times x, and then that's raised to the n minus 1. So I can separate the negative, and I'm going to think about it in an alternate way as n equals 1 to infinity, and then I'm going to have the negative 1 to the n minus 1, and then n x to the n minus 1. So I've separated out the negative 1 raised to the n minus 1, and that's because I just want to be able to see that this is an alternating piece here. It's going to make my terms alternate. And then this is my n to the x minus 1 piece that's left over in the back. So we usually put our alternating piece in the front. So either one of these is fine in terms of finding the power series representation, but what we're still left to do is to find the interval of convergence for g of x. Now we know that the radius of convergence will be the same as the one for f of x because of how we obtained it by doing that differentiation. So the radius of convergence will be 1, but we just need to check the endpoint. So it's either exactly like this, -1 is less than x is less than 1, or we could potentially have equal to signs here depending on what happens at -1 and 1 in this power series. So I'm going to go and make some space. So let's go ahead and write what we know. Well, the radius of convergence for this g of x function is going to be r equals 1. So now we need to check those endpoints. So we need to check what's happening at x equals 1. So that's going to be the sum of n equals 1 to infinity. Now if I let x equal 1 in this power series right here, then all I have left is -1 to the n minus 1 times n. And so here, I mean, by the nth term test, we can see, or the test for divergence, we can see that this particular series is going to diverge. Right? Those terms are just going to bounce back and forth between 1 and -1. So diverge by the nth term test. And if we check x equals -1, then our power series is going to be the sum of n equals 1 to infinity of just n. So if I plug in -1 right here, what's going to happen is I'm going to have -1 to the n minus 1 and -1 to the n minus 1. So every single time those negatives are going to cancel and become a positive. So all I'm going to have left is n. And for the same reason as the previous series, I'm going to have diverge because by the nth term test, the limit of this is going to infinity, not 0. So this too is going to diverge by the nth term test. So the interval of convergence is -1 is less than x is less than 1 as well. In this example, we want to find a power series for f of x equals natural log of the quantity 1 plus x by integrating the power series for g of x, which is 1 over 1 plus x. So this is the exact same series as last time. We're just calling it g of x this time. So I'm going to go ahead and, by magic, replace it with the same work as before. So the only difference is that we're calling this g of x this time instead of f of x. So g of x was 1 over 1 plus x, or 1 over 1 minus -x. So we have our expanded version and then our summation notation version. So n equals 0 to infinity of a, 1, and then -x to the n. And we even had our interval of convergence, which I've copied here. I'm also going to write this in a slightly different way too, just so that we can see there's different ways to write it, and we can really see how it's alternating with that -1 to the n, x to the n. So we can think about it as the -1 to the n, x to the n part, and we can see that alternating piece. Either one is fine, just to have alternate versions or ways to write it. And now we have to think about, well, what is the relationship between g and f? Well, we're actually told it. There's integration involved. So to go from g of x to f of x, which we're trying to write a power series for, we need to integrate. So we can go ahead and write that f of x, which is natural log of 1 plus x, is obtained by doing the integral of my g of x function. All right, so my g of x function is that 1 over 1 plus x. Now technically there would be absolute values. The interval of 1 over 1 plus x would be natural log of the absolute value of 1 plus x. But we can see that this is only happening over -1 to 1. And so here between -1, plugging in -1 to 1 won't cause any domain restrictions for ln requiring us to put absolute value. So to find a power series for f of x, which is natural log of 1 plus x, we are going to integrate my g of x expansion, right, or my g of x summation notation piece. So we'll have, now here, the term-by-term integration, well, I'm going to go ahead and put the constant, the generic constant from a general antiderivative in the front. the antiderivative of 1 would be x, and then the antiderivative or the integral of negative x would be negative x squared over 2, and then we get plus x cubed over 3 minus x to the 4th over 4 plus dot dot dot. So we can do the term by term part, but really we prefer the general term with the summation notation. So this would be the sum. Whoops, actually I'm forgetting that constant. We have to write the constant in the front, right? We don't want that constant included in the general term of summation notation. So the sum of n equals 0 to infinity, so we don't lose the first term when we integrate, we keep it, so n equals 0 to infinity. And then here, in terms of term by term anti-differentiation or integration, what I'm integrating is the x part, and that's why I wanted to kind of rewrite it separately here. So I want to keep the alternating part, negative 1 to the n, by itself. That's not really affected by the integration. The integration applies to the variable x, right? So we're applying the power rule to this x piece right here. Negative 1 to the n is just that constant flipping of the sign. So the antiderivative of x to the n is x to the n plus 1 over n plus 1. And we should always at least kind of check and make sure that it works out with our expanded version. That's kind of the reason to write out both. If we substitute in 0, so I'd have negative 1 to the 0, so that's positive, and then x to the 0 plus 1, so that's x, and then over 0 plus 1, that's 1. That's my first term. If I plug in 1, negative 1 to the 1, now my next term is negative, and then 1 plus 1, that's 2, and then 1 plus 1 again, that's 2. So I can see that my general form works out. Now we've never had a plus c in a power series representation before, so we don't want a plus c right now. We'd like to eliminate it by solving for the value of c. So to solve for c, I'm going to do that work over here in the corner. So to go ahead and solve for the value of c, what we're going to do is recognize that what we're saying is that natural log of 1 plus x is equal to this c plus the sum of n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. Of course, we're saying that this is true within the interval of convergence, so between negative 1 and 1. So let's go ahead and substitute in a value for x between negative 1 and 1 that will allow us to solve for this missing c. Well, the easiest thing to go ahead and plug in this case is going to be x equals 0. So if we go ahead and let x equal 0, we get natural log of 1 on this side. Well, natural log of 1 is 0, so I get 0 equals c plus, and now here if I go ahead and plug in 0 into x, that's going to zero out this whole thing right here. So we're just going to sum up 0 a bunch of times. So we get that the value of c is 0. So we can eliminate c because c is now 0, and we can say that our power series representation, right, to conclude here, our power series representation for ln of 1 plus x is just the sum of n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. Earlier in this unit, we posed the question, why would we bother to develop a Taylor polynomial for a nice function like 1 over 1 minus x? So normally we would do it for a transcendental function, because 1 over 1 minus x, that's kind of already easy to work with to maybe evaluate. But notice how we obtain natural log of quantity 1 plus x for our integral, right, in that previous example. So the Taylor series representation allowed us to integrate and obtain a transcendental function that we can now use to approximate things like natural log values. So there was a reason to go ahead and develop first a Taylor polynomial and then a Taylor series for 1 over 1 minus x. And it's in that we can differentiate and integrate to get maybe some other more complicated function represented as power series. In this next example, we're told to use integration to find a power series representation for tangent inverse of x and find the interval of convergence. Then use the first 4 terms of the power series to approximate tangent inverse of 1. Now this problem is a little bit trickier because we're not told specifically what to integrate. It's just use integration to find a power series for tangent inverse of x. So we have to know our relationships between functions and their derivatives and their integrals. So let's start by writing tan inverse of x. Well, tangent inverse of x is the integral of 1 over 1 plus x squared dx. So we have to know that the integral of 1 over 1 plus x squared gets us to tangent inverse. And 1 over 1 plus x squared has that a over 1 minus r form to be able to express it as a geometric power series. So here I'm going to rewrite it so that I can really see it as 1 minus negative x squared. So my starting term, my first term is 1, my common ratio is negative x squared. So in other words, we're going to be integrating 1 minus x squared plus x to the 4th minus x to the 6th plus dot 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 dx. So if we think about the term by term integration here, again we're going term by term, we multiplied by negative x squared, or in that summation notation format, we're going to integrate the sum of n equals 0 to infinity of a, and then my common ratio was negative x squared to the n dx. So this is my condensed summation notation version here, a r to the n. Alright, so now let's go ahead and think about the actual integration part. First, let's go ahead and think about it like term by term here. So we're going to put that constant in the front, and then the antiderivative of 1 is x, so we're going to have plus x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot dot dot, and then is equal to, so here if I integrate, I'm going to go ahead and keep that c in the front, and then plus the sum of n equals 0 to infinity. Now here's where maybe we want to think about how exactly we would rewrite this. Maybe before we integrate will help us out a little bit. So here we can think about this as negative 1 to the n and then x to the 2n. So this piece right here is negative 1 to the n and then x to the 2n. So taking the negative 1 to the nth power, x squared to the n is x to the 2n. So when I attempt to do my general antiderivative of the general term, well, that doesn't affect the n portion, so we're going to leave that negative 1 to the n. So it's still going to alternate, and then we're going to add a power, so we're going to have x to the 2n plus 1 over 2n plus 1. So this, if we follow the chain of equal signs, that's why it's so important to accurately use your equal signs. Tan inverse is the integral of 1 over 1 plus x squared, which we can think of as this a over 1 minus r, where a is 1 and r is negative x squared. So from here to here, we're writing out the power series expansion and term by term. And then here is the power series represented in summation notation. And so we can integrate each version, right? And so the expanded version will kind of help us to check to make sure what we've done over here in the summation notation version is correct. So if I plug in 0 into n, negative 1 to the 0, that goes away, that's just positive 1. If I plug in 0 here into the 2n, I get x to the 1, and then on the bottom I'd get a 1. And then if I start to plug in 1, then I have a negative x to the 3rd, so 2 plus 1, 2 plus 1. So I can see that's going to generate those odd numbers. 2n plus 1 will generate those odd powers and those odd denominators. The only thing left now to finish the first part of this question, to find the power series representation for tan inverse, is to solve for c. So again, if we follow that chain of equal signs, we know tan inverse should be equal to this power series representation for any value in the interval of convergence. So let's take a second and think about the interval of convergence first for my 1 over 1 minus negative x squared portion. So here, if we go ahead and think about the interval of convergence for this part, since it's geometric, that's when the absolute value of negative x squared is less than 1, and that's going to be just absolute value of x squared is less than 1, which is only happens between negative 1 and 1. So for any x value that I choose in this interval of convergence, these should be equal to one another. So let's go ahead and pick 0 right smack in the middle, and that'll be easiest to help us solve for our value of c. So to solve for c, we'll go ahead and let x equal 0, again like last time. Well, tangent inverse of 0 is 0, and then if we plug that x equals 0 in on the right hand side, just like last time, this x will just zero out this whole thing. So it'll be plus the sum, I'm just going to put of 0. So c is equal to 0. So my power series representation will then be just the summation part. So sigma sum of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. So this was the interval of convergence for just the 1 over 1 plus x squared part, but we want to find the interval of convergence for the actual tan inverse power series, this one over here. And we know they're going to have the same radius of convergence, but we'll just need to test the endpoint. So we're looking at checking negative 1 to 1. So I'm going to make some space here. Alright, so let's go ahead and check our endpoints, right? So we must check endpoints, and that would be for the tan inverse interval of convergence, right? Tan inverse of x interval of convergence. So that's testing the negative 1 and 1, so we can try what happens when x equals negative 1, and we're checking that up here in our power series answer. So we'll have the sum of n equals 0 to infinity, and then we have negative 1 to the n, and then negative 1 to the 2n plus 1 over 2n plus 1. From here, we'll go ahead and look at the simplification, because I've realized that's where students kind of tend to struggle. So we have n equals 0 to infinity of negative 1 to the n, negative 1 to the 2n, negative 1 to the 1 over 2n plus 1. So all I did was take negative 1 to the 2n and negative 1 to the 1, because when you put these back together you'd add them with the same base. And I'm doing that to recognize that negative 1 to the 2n is just positive 1. So I'm raising a negative to even powers, so this is just positive 1, that cancels. So my series is really n equals 0 to infinity of negative 1 to the n plus 1 over 2n plus 1. So I can see I'm still alternating, because negative 1 to the n plus 1 creates alternating, and then I have 1 over 2n plus 1 as like my a sub n. So to determine whether this type of series converges or diverges, we want to think about the alternating series test. And so here, this is going to converge by the alternating series test. So we have by the alternating series test converges, and we can see, you know, it alternates and the terms are decreasing, right? A sub n is less than a sub n plus 1 every single time, because I have this 1 over 2n plus 1. So by the alternating series test, we are going to have a convergent series. The limit goes to 0, the terms are decreasing, I'm alternating. And then we can go ahead and check what's happening at x equals positive 1. So that would give us the sum of n equals 0 to infinity of negative 1 to the n. And then here, if I plug in, up here, if I plug in x equals positive 1, this whole term is just gone. Like 1 to the anything is 1. So we're really just doing negative 1 to the n over 2n plus 1. So by the same reasoning, this is alternating, and the a sub n is 1 over 2n plus 1. This is also convergent by the alternating series test. So that means that we do include the endpoints. So what our summary is from this is that the interval of convergence for tan inverse of x is negative 1 is less than or equal to x is less than or equal to 1. Now, to scroll up a little bit, the last part of this problem is use the first 4 terms of the power series to approximate tan inverse of 1. So remember, we're like circling back to, all of these power series, or if we cut them off like a Taylor polynomial, were used to approximate these transcendental functions. So use the first 4 terms to approximate tan inverse of 1. So I'm just going to go ahead and come over to the left here and write out what the first 4 terms are. So what we're saying is tan inverse of x is approximately x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. So this is essentially a Taylor polynomial, one that should look familiar, right? We did derive this previously. And we're going to use this to approximate tan inverse of 1. So tan inverse of 1 is approximately 1 minus 1/3 plus 1/5 minus 1/7. And if you do substitute that into a calculator, it's about 0.7238 as the approximation for tan inverse of 1, using the first 4 terms of the power series. And if we chop it off, right, it's a polynomial now, and since this was centered at 0, it is a Taylor or Maclaurin polynomial. In this example, we have to find a power series representation for 1 over 1 minus 4x squared and its interval of convergence. So this one is actually pretty straightforward because we are just finding a power series representation for something that already looks geometric, that a over 1 minus r look. So here we just have to recognize what a and r are. So my a value is 1, so my expansion will start with 1, and then to get from one term to the next, my common ratio is 4x squared. So positive 4x squared because it's a over 1 minus r, so it's going to be plus 4x squared, and then if I multiply again, plus 16x to the 4th, plus dot dot dot. I'll just write a few terms of the expansion, but ideally we want the summation notation, so we'll start from n equals 0 to infinity of that a value, 1, and the common ratio is 4x squared to the n. So this right here is my power series representation. That's all we're being asked to do for the first part. And to find the interval of convergence, well, if it's geometric, the interval of convergence is when the absolute value of r, the absolute value of 4x squared, is less than 1. Well, 4 is already positive, so we can take it out of the absolute value bars and divide by it, so the absolute value of x squared is less than 1/4. And here, the inequality solved is going to give us negative 1/2 is less than x is less than 1/2. So we can see that it wasn't just x here, it was x squared, and then the square root of 1/4 is that 1/2, so we're going to be, our x values are going to be trapped between negative 1/2 and 1/2. So this is going to be my interval of convergence, and then this is going to be my power series representation. In this last example, we want to find a power series representation for f of x equals the quantity x over 2 minus x all raised to the 3rd, and find its radius of convergence. Now this one's going to be a little bit trickier because we don't have right away that general form of a over 1 minus r, and we're going to have to think about how it connects somehow to differentiation or integration. The first thing I'm going to do is try to establish that 1 in the numerator that we need, or that constant, that a, by rewriting this as x to the 3rd in the front, and then times 1 over 2 minus x all cubed. So again, I just took x cubed and kind of brought it out, and now I have a 1 there, and then the 2 minus x is still raised to the 3rd. So I can also think about this as x cubed times 1 over 2 minus x cubed. Now what we're going to do to find this power series representation for this whole function is I want to think about it as these two separate pieces, and really just find a power series representation for 1 over 2 minus x cubed and then multiply it by x to the third. So our goal is to find a power series representation for this second part, 1 over 2 minus x cubed. And to do that, we're going to think about how it is the derivative, or actually the second derivative, of 1 over 2 minus x. So we're going to start by focusing on, I'm going to call it a different named function. I'm going to call g of x 1 over 2 minus x. So we're starting with that a over 1 minus r form, or close because it's 2, and we'll work with that. And we want to see how we can differentiate this 2 times to get something that looks like 1 over 2 minus x cubed power series. So let's think about differentiating this. So this is 2 minus x to the negative 1. So when I take the first derivative, I will get negative 2 minus x to the negative 2 times the derivative of the inside, right, negative 1. And so what I end up here with is just 2 minus x to the negative 2, or that's 1 over 2 minus x squared. Well, I need 1 over 2 minus x cubed, and that's why we're going to have to take a second derivative to get there. So the second derivative is negative 2 times 2 minus x to the power of negative 3 times the derivative of the inside, which is negative 1. So I can see that this is 2 over quantity 2 minus x cubed. So my original function that I started with was geometric, 1 over 2 minus x. And by differentiating it twice, I ended up with something pretty close to 1 over 2 minus x cubed. I'm just off by this 2. So what that means is I can think about 1/2 of g double prime of x will be equal to 1 over 2 minus x cubed. So if I just think about multiplying both of these sides by 1/2, the 1/2 and the 2 will cancel and get me that 1 on top. So bringing it back over here, what I know then is that f of x is equal to x cubed times 1/2 of g double prime of x. So if I can find a power series representation for g double prime of x, that's going to be multiplied by 1/2 and x cubed to get me my power series representation for f of x. That brings us back over to g of x, 1 over 2 minus x. We want to start by writing this as a power series and then differentiate and differentiate again. So here I need to set this up to have a 1 in the bottom left-hand corner. So I'm going to divide the numerator and denominator by 2. So this is equivalent to 1/2 over 1 minus x over 2. So we're looking at our a value as 1/2 now and our common ratio as x over 2. So the power series representation for this is the sum of n equals 0 to infinity of a, which is 1/2, and then r, which is x over 2 to the n. So a, r to the n. So this is my power series representation for g of x, and we're trying to get to g double prime of x, so we need to differentiate. Notice I didn't bother writing the expanded version here. We can just jump straight to the summation notation. Now to get to g prime of x, taking the derivative, I can go ahead and differentiate this general term right here. So I can go ahead and bring the n to the front, so write the sum of n equals 1 to infinity. We lose that starting index when we differentiate. So we'll have 1/2 n x over 2 to the n minus 1. So bring the power to the front, reduce the power by 1. The derivative of the inside, the derivative of x over 2 is 1/2. So this is just 1/2 x, right? So the derivative of x over 2 is just 1/2. So a nicer way to kind of put that together is n equals 1 to infinity of 1/4 n, and then x over 2 to the n minus 1. So let me go ahead and kind of section this off for a second. And then now g double prime of x, we can go ahead and differentiate here one more time. So we'll end up with the sum of n equals 2 to infinity. We're going to move the starting index up again. And now here I would bring that n minus 1 to the front, so I have 1/4 n already there, times the quantity n minus 1. Then we have x minus 2 to the n minus 2, so I subtract 1 from the exponent, times the derivative of the inside, which is again 1/2. The derivative of x over 2 is 1/2. So we're looking at the sum of n equals 2 to infinity of 1/8 n times n minus 1 times x over 2 to the n minus 2. So that is g double prime of x, right? That is g double prime of x. So if I want the power series representation for f of x, we can pick up where we left off. So I'm going to go ahead and kind of like draw a wavy line here. So x cubed, I'm going to pick up where I left off here. So I have x cubed times 1/2 times g double prime of x. Well, if we follow this equality here, g double prime of x all the way across is this power series representation. So it's the sum of n equals 2 to infinity of 1/8 n quantity n minus 1 x over 2 to the n minus 2. So here, this is my power series representation for f of x almost. I want just one power series where I'm going to multiply this 1/2 and this x cubed into the summation notation. So from here, I'm going to go ahead and pull this up. I have the sum of n equals 2 to infinity of 1/16. So I'm multiplying the 1/2 and the 1/8. And then I have n minus 1. And then let's go ahead and think about this x cubed and then x over 2 to the n minus 2. So I'm going to pull the x cubed in, and I'm going to rewrite this x to the n minus 2, x over 2 to the n minus 2 as x to the n minus 2 over 2 to the n minus 2. And the reason for that is because I can combine these together. If these x's have the same base, I can add their exponents. So this is x to the n plus 1. So let's see where we're at here. So we have n equals 2 to infinity. This is 1 over, I'm going to write this right now as 1/2 to the 4th for a second, and we'll see why. And then I have, whoops, that looks like 2 times 4. There shouldn't be a dot there. So 1/2 to the 4th, n minus 1. I have x to the n plus 1. Again, I am adding those exponents together of the x. And then on the bottom, I have 2 to the n minus 2. So I wrote 16 as 2 to the 4th because I'm going to do that same thing here. Since these have the same base too, I can add their exponents. So this is going to end up looking like 2 to the n plus 2. So I have the sum of n equals 2 to infinity of n minus 1 over 2 to the n plus 2, and then x to the n plus 1. So this is my power series representation for f of x. So if we follow this back up, right, f of x was x over 2 minus x cubed. We pulled out the x cubed. That's 1/2 minus x quantity cubed, which we wrote as 1/2 minus x cubed. And then we figured out that 1/2 minus x cubed, that's a half of what I called g double prime of x. So g of x was 1/2 minus x. Taking the derivative twice, we got 2/2 minus x cubed. So 1/2 minus x cubed is multiplying both of these sides by a half. And so we replaced g double prime of x with its series representation, right, after we applied the AR to the n, took its derivative again. We replaced g of x, so this g double prime of x, with this g double prime of x right here. And then we distributed in the 1/2 x cubed and then just cleaned it up a little bit. So all of this is equal to f of x. This is the power series representation. But the second part to the question is find its radius of convergence. Okay, so now here's the thing. G of x, 1 over 2 minus x, that's geometric. We can find its radius of convergence simply by doing, let me go ahead and switch colors here. So for g of x, we can find its radius of convergence by doing the absolute value of x minus 2, the absolute value of the common ratio. When is that less than 1? Well, when the absolute value of x is less than 2, if I multiply it by 2, so the radius of convergence is simply 2. Right? The radius of convergence is simply 2. That's for g of x, and that's for g prime of x, and that's for g double prime of x. So we know that if we differentiate a function represented by a power series, all those derivatives are still going to maintain the radius of convergence. So this is the radius of convergence, r equals 2, for g of x and g prime of x and g double prime of x. But our function was combined with x cubed times 1/2. So this part right here was my g double prime of x part. So this part was g double prime of x, but I have this extra piece here, 1/2 x cubed. So it's not just the derivative, it has some extra stuff associated with it. So to find the radius of convergence for that, we no longer have a geometric series. We're going to have to use the ratio test to find the radius of convergence for our resulting power series, because our theorem only told us for sure that strict derivatives were maintained that radius of convergence, but multiplying by the 1/2 and the x cubed doesn't follow that theorem. So let's go ahead and apply the ratio test to find the radius of convergence. So we'll go ahead and do the limit as n approaches infinity of here. We're going to go ahead and do a sub n plus 1 over a sub n. So that's replacing all these n's with n plus 1's. So I'm going to have n plus 1, n. So I'm replacing this n, this n. This right here would become x to the n plus 2. And then the denominator, if I plug in an n plus 1 here, I'm going to have 2 to the n plus 3. And then divided by a sub n is like multiplying by this reciprocal here. So the other pieces are going to look like x to the n plus 1. And then the 2 to the n plus 2 will go on the top. And the n minus 1 will go on the bottom. So we need to solve when is this less than 1 in order to apply the ratio test here. So now let's go ahead and kind of think about what happens. So the n plus 1 and n and n minus 1, all of that goes to 1. So I'm going to just like cross it out. All of that just goes to 1 as n goes to infinity. And then let's see what's happening to the remaining parts here, see what we can cancel. So we have x to the n plus 2 and x to the n plus 1, so there's one extra x on the top. So these will cancel, and we'll just have an x left on the top. And then we have 2 to the n plus 3 and 2 to the n plus 2, so there's one extra copy of 2 on the bottom. So this will cancel and this will cancel. So what I have left here is just x over 2 is less than 1. So again, we evaluated the limit and canceled things out at the same time. So the limit part where n plus 1, n minus 1, that's the same ratio, that'll go to 1. And then there's one extra copy of x on the top and one extra copy of 2 on the bottom. That's all that's going to be left over. So that means that the absolute value of x is less than 2. So that does imply that the radius of convergence is 2 for our power series representation for f of x. So here's part of my answer, and then the actual power series part is over here.